Last time we discussed what is a subset, what is proper subset. We discussed some examples. Now let us talk about Venn diagrams. What are Venn diagrams? We represent sets A and B by circles. For example, on this picture over here, A is a subset of B. On this picture, 6.11, A is a subset of B, B is a subset of A, therefore A is equal to B. Now, over here, these are examples when A is not a subset of B. In picture A and B do not have common points. On picture B, there are points on A which are not in B. And now on picture C, B is a subset of A, not A is a subset of B. Venn diagrams is convenient to use, for example, if we wish to show that Z, the set of all integers, is a subset of Q, and Q, the set of all rational numbers, is a subset of R. Next portion of this section, we are talking here about operations on sets. We start with the following operations: union, intersection, difference, and complement. Please take a look at these Venn diagrams. By the way, we start with a so-called universal set. Universal set, we mean a set that contains everything which we discuss in our problem. So, suppose A and B be subsets of a universal set U. What is union of A and B? Union of A and B, denoted by A union B, is the set of all elements that are in at least one of A or B. On this picture, by blue rectangle, we denote universal set. And now the shaded region is union of A and B. By intersection, we mean the set of all elements that are common to both A and B. Over here, intersection. Difference, B minus A, denoted by B minus A, is the set of all elements that are in B and not A. Over here. Finally, by complement of A, denoted A complement, we mean the set of all elements in U that are not in A. So over here, we shade everything outside A. And symbolically, this is what we mean by union, intersection, difference, and complement. So folks, please take a look at this. Any questions? Think about questions.
So for how many sets is a Venn diagram recommended? Like how many sets?
Well, say if we have few, one set, three sets. Now, later on, we will see that, well, especially in some problems, Venn diagrams help a lot. Right now, we use Venn diagrams as illustrations. We cannot, by the way, we cannot really use Venn diagrams to prove something. We basically use Venn diagrams to come up with a proof or to illustrate a rule. Okay, next. So here we have a pretty basic example, universal set, A, B, C, D, E, F, G. He is A, he is B. find union, intersection, difference, complement. Here is the answer. So I would say union and intersection is pretty self-explanatory. Talking about B minus A, we remove from B elements from A. So we don't remove A from B because there is no A here. We don't remove C from B because there is no C here. We remove E because E is here, and we remove G because G is here. So what is left is just D and F. Talking about A complement, we remove elements that are in A from the universal set. And here is the result. Now, in this course, we will use integral notations. And here is a reminder what we mean by AB in parentheses, AB in brackets, and so on. In short, parentheses means we do not include endpoints. Brackets, we do include endpoints. For example, here, A comma B in parentheses means X is strictly between A and B. If we have in brackets, A is greater or equal to A and lesser or equal to B. Now we can combine parentheses and brackets. In this example, we do not include A, we exclude A, and we do include B. Here we have a similar example when we include A and exclude B. By infinity, we mean the following. X is strictly greater than A. Negative infinity, X is strictly lesser than B. By the way, guys, over here we have a misprint. So let us start with this example. We include A. So X is greater or equal to A. Over here we have a misprint. We should exclude negative infinity and include B. So should be parentheses here and bracket here. Means X is lesser or equal to B. Guys, any questions here? So once again, this is a misprint. Should be all the way around. Parentheses, brackets. And by the way, you can make a remark. We never include infinity because infinity is not a number, it's a symbol. So in all four examples, we have parentheses attached to infinity. Next, we have some examples. Here's A, here's B, find A union B, A intersection B, B minus A complement. Well, here's how we do it. So in order to answer these questions, it's convenient to draw pictures. By A, we mean the following shaded origin. Black dot means we include 0. Empty dot means we exclude -1. Similarly here, we include 0, we exclude 1. Now, what is A union B? We shade everything from -1 to 1. So A union B will be the following interval from -1 to 1, and we exclude -1, we exclude 1. It's exactly what is written here. From -1 to 1. Now, by intersection, we mean just 1 point, 0, because there are no other common points. So it's 0. Now, we subtract all points that are in A from B. But know that we have only one common point, 0. Therefore, B minus A will be an interval from 0 to 1, where we exclude 0 and exclude 1. It's exactly what is written here. Lastly, complement of A means we consider all points to the right from 0 and to the left from 1, and we exclude 0 and include -1. So it's exactly what is written here. We exclude 0 and we include -1. From -infinity to -1, union from 0 to infinity. Folks, any questions here?
Sorry, can you go over the complement one again?
Yes,
on
yes,
the
yes.
upper page.
Yes, complement. So a complement of A. A is the following: interval from -1 to 0. And by the way, we exclude -1 and we include 0. This is A. Therefore, complement will be this portion to the right from 0 and this portion to the left from -1. Moreover, we will exclude 0 and we will include -1 for the complement, correct?
Yeah.
Because complement means everything which is not in our set. In our case, outside our interval.
Okay, I got it.
Next, here we discuss unions and intersections of indexed collection of sets, which means instead of considering union of just two sets or intersection of two sets, we consider n sets. So by union of sets A0, A1, A2, and so on, by the way, here we allow to consider infinitely many sets. We mean the following: all elements from the universal set such that X is from AI for at least one I from 0 to n. Similar definition we have for intersections. Think about questions.
What does I mean here? Is this the I like the first set, second set?
So remember here we denote our sets not by A, B, C, D, but by A0, A1, A2, and so on. So I can be here either 0 or 1 or 2 and so on.
Yes. And for infinitely many sets, what does it mean? Is the universal set infinite or?
Yes and no. I can give you a very simple example. Imagine that all sets are equal and each set is equal to the following set, 1, 2. And universal set consists of just, say, 3 elements, 1, 2, 3. You see what I'm talking about?
Yes.
Any other questions?
Can you explain the difference between why it's at least one non-negative integer versus all non-negative integers? Or at least I through, or actually no, sorry, not for the infinity one, for the ones where it's at least one I versus for all I.
Are you talking about line number 1 and line number 3?
Yeah, that's what I mean, yeah.
So here, by union, what we mean by union is the following. We put together all elements from all sets. Say, imagine that instead of sets, we have boxes with balls. By union means we put all these balls in one basket. By intersection, we select only common balls.
So I understand the difference between intersection and union, but what is it in the in the union one? It says for at least one. I guess that's the part I'm confused about.
Take a look at Venn diagram. So the whole shaded region is union.
Right.
All these points are indeed either in A or in B or both.
Okay.
A or B or both means in at least one.
Right, so you're saying that it could be a union of A and B if they just shaded the region A? Or because I don't think.
No. We have to shade the whole thing. So we put together 3 types of sets. Elements are in A, but not in B. Then elements that are in B, but not in A. And then elements that are in A and in B. Everything.
Oh, okay. Okay, that's like the union rule. Okay, I got it.
Well, this is union rule.
Right, yeah.
About union.
Well, I'm saying it's the A, you're adding A and B, and then you're adding the intersection.
So in other words, we have 2 baskets. We just put everything together. It does include intersection.
Okay, yeah. Okay, I got it.
It includes everything.
Yep, I got it.
All right, now, next. So let us consider the following sets. AI is an open interval from -1 over I to 1 over I. We want to find this, and we want to find this. So let us talk about the union of finite number of sets. Observe that when we increase I, the interval shrinks. It becomes smaller and smaller and smaller. But also observe that if we consider AI and AJ, if J is greater than I, AJ is completely in AI. For example, A3 is completely in A2, means A3 is a proper subset of A2. A2 is a proper subset of A1. Or say A10 is a proper subset of A7. Keeping this in mind, the union of A1, A2, A3 is A1, which is the interval from -1 to 1. Talking about intersection, the intersection will be A3, which is the interval from -1/3 to 1/3. So union is this, intersection is this. Guys, any questions about this example?
Could you clarify what you meant by proper subset?
Proper subset means A is completely inside B, but there are elements in B that are not in A.
Oh, okay, I got you.
How did you know that that they were subsets of each other?
Well, very good question. You can, for example, draw a picture. For A1, we'll get interval from -1 to 1, correct? For we'll get an interval from -1/2 to 1/2. And if you draw a picture, interval from -1/2 to 1/2 is a proper subset of the interval from -1 to 1.
Okay. And then for the intersection, can you go do that again? And
yes, for intersection, again, think about this. A3 is completely inside A2. A2 is completely inside A1. In other words, A3 is a proper subset of A2, and A2 is a proper subset of A1. There is no escape. Their intersection is A3. Union is A1, intersection is A3.
Oh, okay, I see.
Now, talking about question B. For the union of all such sets, the union of all such sets will be the integral between -1 and 1. Because once again, when we increase I, the integrals shrink. Moreover, the next integral is a proper subset of the previous integral. So the union will be A1, the integral between -1 and 1. It's exactly what is written here. Talking about intersection, note that since our intervals shrink to 0, the only common element will be the number 0. So the intersection is the set that consists of just one element, 0. Okay, next. Empty set, or we call it null set. Null set or empty set is a set that does not have elements. For example, the intersection of these two sets is the empty set. And this is how we denote the empty set. Or the set of all real numbers that satisfy the equation x squared is equal to -1 is the empty set. Here's another example. The set of all real numbers that satisfies the following double inequality. X is greater than 3 and lesser than 2. It's the empty set. Guys, any questions about empty sets?
For the empty set, do you also accept the notation of like just curly braces with no elements inside?
No, we do not put here curly braces.
I mean the curly braces, but like nothing is inside of the curly braces.
Yes, if I understand you correctly, we can just put curly braces and there is nothing between curly braces. So it's another way to denote an empty set, yes. But standard notation is this. Next, partitions. Let us start with the following. Two sets are called disjoint if and only if they have no elements in common. Means A and B are disjoint if and only if their intersection is the empty set. For example, these two sets are disjoint because they do not have common elements. Suppose we have several sets. These sets are called mutually disjoint or pairwise disjoint or non-overlapping if intersection of AI and AJ is the empty set whenever I is not equal to J. For example, let us consider sets A1, A2, A3. Are they mutually disjoint? Yes, they are mutually disjoint because A1 and A2 have no common elements, A2, A3 have no common elements, and A1, A3 have no common elements. However, sets B1, B2, B3 are not mutually disjoint because B1 and B3 have a common element 4. Guys, questions here? Next. Here's what we mean by partition. It's easy to explain partition if we use, say, Venn diagrams. We have some set A, we split it into several non-overlapping subsets. This is what we mean by partition. Here's a rigorous definition of partition. A finite or infinite collection of non-empty sets, A1, A2, and so on, is a partition of A if and only if A is a union of these sets and sets A1, A2, A3 are mutually disjoint. For example, A is the following set: 1, 2, 3, 4, 5, 6. Then A1, A2, A3 is a partition of A because union of A1, A2, A3 is A, and A1, A2, A3 are mutually disjoint. Here's another example of partition. Let us consider Z, the set of all integers. Then T0, T1, T2 is a partition of Z because union of T0, T1, T2 is Z, and T0, T1, T2 are mutually disjoint. The fact that the union is Z and they are mutually disjoint follow from the quotient remainder theorem. Guys, any questions here?
So is a partition a type of set that includes sets? Like a set within a set? Like, because it's T0, T1, and T2 are all sets.
Yes, partition is a set where elements are sets.
Oh, okay, okay.
Yes.
So if the individual sets are not mutually disjoint, then they can't form a partition?
No, they do not form a partition. They have to be mutually disjoint. In other words, if A1 is 1, 2, 3, then A1, A2, A3 is not a partition.
So mutually disjoint means that there is no intersection. There are no...
Yeah, mutually disjoint means we pick any two sets. They do not have common elements. Next, what is power sets? We start with a set A. By power set, we mean the set of all subsets of A. Here's an example. Suppose A is the following set, X, Y. A consists of just two elements, X and Y. Then the power set consists of 4 sets. We always start with the empty set because the empty set is a subset of any set. So empty set, then the set that consists of just X, the set that consists of just Y, and the set that consists of both X and Y. So what we see in front of us here is the power set of this set. And by the way, one can show that if our set consists of n elements, its power set has two 2nth power elements. For example, our initial set consists of 2 elements. Its power set has 2 square elements, 4. Any questions here?
So can you go over power set again? Sorry, really
Power
quickly.
set, yes. Power set is the set of all possible subsets.
Okay.
All of them. So note that the empty set is a subset of this set. Set number 2 is a subset of this set. Set number 3 is a subset of this set. And set number 4 is a subset.
Okay, I got it.
And
Okay.
there is nothing else.
Okay.
Other questions here?
I've got a question.
Yes.
So is the null set a subset of any set?
Yes. As I said, empty set is a subset of any set. Yes. Other questions? So once again, if the original set consists of n elements, its power set has 2 2nth power elements. And lastly, Cartesian products. By ordered n-tuple, we mean this: x1, x2, and so on, xn. Important. 2 ordered n-tuples are equal if and only if x1 is y1, x2 is y2, and so on. For example, is this equal to this? No, because 3 is not equal to 4 and 4 is not equal to 3. Are these triples equal? Yes, because 3 is square root of 9, negative 2 squared is 4, and 1/2 is 3/6. So no for A, yes for B.
Okay, I have a question.
Yes, yes.
So if we have a tuple 1, 2, 3, and
Yes.
the second one is 1, 2, 3, 4, are
No.
these two equal?
No, they are not equal, because to make sure that they are equal, they have to have same number of.
Same. Okay. So
Yes.
it's an array.
Very good point.
Okay.
So n-tuples 1, 2, and 1, 2, 3 are different. And finally, by Cartesian product of several sets, we mean the set of n-tuples where A1 is from A1, A2 is from A2, and so on, AN is from AN. For example, let us consider 3 sets. A1 is XY, A2 is 1, 2, 3, A3 is AB. Find A1 cross A2. A1 cross A2 means we plug in each element from A1 for position number 1 and each element from A2 for position number 2. So here are all possibilities. We start with X. X1, X2, X3. We are done with X. Then we do Y. Y1, Y2, Y3. This is what we mean by A1 cross A2. In the same fashion, we consider A1 cross A2 cross A3. So, which means A1 cross A2 is this set. Now elements are this, 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 and so on. Therefore, if we consider cross A3, we'll get the following. We start with element number 1, x, 1. And for position number 2, we put elements from A3. So here, x, 1, A, x, 1, B. Then we do same for x, 2. X, 2, A, x, 2, B, and so on. However, for Cartesian product A1, A2, A3, we consider all triples over here.